Hello everyone. I want to discuss section 8.2, hybrid atomic orbitals. We will be using multiple videos to cover this section. In this first video, the learning objective is explain the concept of atomic orbital hybridization. As I've mentioned in previous videos, the models we make to describe molecular behavior sometimes only work so far, and then we see that they don't work very well. So we'll start by looking at valence bond theory, which is the idea we had discussed in the previous section, and see where we have some shortcomings there. So if we use valence bond theory to try to predict the behavior of, say, a water molecule, what we see is it doesn't do a very good job of showing us what would happen. So with valence bond theory, we would predict, as we're showing in this picture right here, we would predict that we have a bond angle of 90 degrees for the water molecule. And we know that that is not true experimentally. And in fact, we've already come up with the VSEPR model that does a much better job of predicting that shape than valence bond theory does. So the prediction doesn't work very well. Also, you'll notice that the colorations here aren't great, so we would expect them to match. I'm not sure why your book has done it in that way. That is not a failure of this model. The failure is that it doesn't predict the correct shape. There is a way to have made that work in this case if that was an issue. So how we make this work is by reconsidering what kinds of orbitals exist when we have bonding that goes on. So the orbital concept, again going back to Module 6, is expressed by a mathematical wave function, which again we use the symbol psi to indicate. I think we skipped over some of the details of that, and we don't get into a lot of the details in this course. So we have some wave-like properties that describe where the electron is, and essentially the wave functions are telling you things like the shape of s orbitals, the shape of p orbitals, etc. So the idea here is we have a new kind of orbital that can exist when we have a bond. That is not just the orbital of one and the orbital of another. It's a mixture of the two. We call this hybridization. So hybridization in the context of hybrid atomic orbitals is the combination of atomic orbitals to form a new type of orbital. This is done by something called the linear combination of atomic orbitals, abbreviated LCAO. And the idea that the linear in that means that we take, 1 plus 1 equals 2. So if we have combined two things, we get two things. And we'll go through the details of that here shortly. But what we end up with are things that are called hybrid orbitals. And we'll get to the details of this later, but it turns out that the hybrid orbital that you come up with does end up working with VSEPR theory, working with the experimentally determined shapes of water molecules. So we do get something close to what would be predicted with this model compared to valence bond theory. Okay, so I'm going to end by discussing some of the important ideas for the concept of hybrid atomic orbitals. First of all, they do not exist in atoms. Hybrid atomic orbitals would only exist in covalently bonded atoms. So if you have just an oxygen by itself, it would have the kind of atomic orbitals that we discussed in Module 6. If it were within a covalently bonded molecule, it might have hybrid orbitals. The shapes and orientations of hybrid orbitals are not the same as those that exist in atomic orbitals and isolated atoms. So we don't have spherical shapes. We don't have kind of the symmetrical lobes that we had. We have different kinds of shapes here. We create a set of hybrid orbitals by combining atomic orbitals. The number of hybrid orbitals in that set is equal to the number of atomic orbitals that were combined to produce the set. So if you combine, let's say if you combine 2 orbitals, you'll get 2 orbitals. If you combine 3 orbitals, you'll get 3 orbitals. These orbitals that you're combining are on the same atom. So you would be combining, say, some p orbitals or an s orbital and some p orbitals to get these new types of orbitals. When this is done, you'll get hybrid orbitals that have the same shape and energy when you have this new combination. You end up getting results here that are consistent with VSEPR theory in terms of predicting the geometry of the molecules that are formed. Okay, so they end up leading to that. And then when you form hybrid orbitals, they overlap to form sigma bonds. If they are not hybridized, they can overlap to form pi bonds. So hybrid leads to sigma, non-hybrid leads to pi. These ideas we'll be discussing in the forthcoming videos. So these are some of the main ideas to understand about hybridization. And then in the next video, we'll look at specific examples of types of hybridization that can